Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this NPTEL course on Circular Economy for Sustainable Buildings. We had already seen how we can reduce water and energy consumption in buildings through various strategies like using appropriate eco-sensitive accessories, then using innovative gadgets like the Varka water or gravity light and so on. And then last class we saw how we can reduce embodied carbon in the built environment through appropriate choices that we make. And we saw the first 5 ways of doing it, and we will continue with that in this class. So, the sixth method or sixth way in which we can reduce embodied carbon is through framing policies, regulations and initiatives and following the policies, regulations and initiatives which are already in place. So, India already has a number of planned policies for reducing carbon emissions. Why? Because in 2015, the Paris Agreement said that we have to limit global warming by 2 degrees above pre-industrial revolution areas. So, what is India taking action in order to comply with that? It intends to reduce emission intensity by at least 33% by the year 2030 and also to generate at least 40% of electricity from non-fossil fuel sources by 2030. We have already seen which are the non-fossil fuel sources, that is solar, wind, hydro, geothermal and so on. Also, in order to comply with the Paris Agreement, India intends to create an additional carbon sink of about 2.5 to 3 billion tons. So, what all are the policies that India has in place? There are a number of policies which are like the NBC, we already saw Bureau of Energy Efficiency, ECBC, commercial, ECBC for residential, which is Eco-Niwas Samhita, star rating of commercial building, star rating of gadgets, green building rating systems such as LEED India, Griha, EDGE and so on, initiatives of the Ministry of Housing and Urban Affairs, the National Mission on Sustainable Habitat, the Green Credit Program and retrofitting existing buildings. So, India has also launched the National Hydrogen Mission in 2021 and that is expected to spearhead India towards the status of becoming a hydrogen exporter to the world. Though India was a net importer of crude oil, it will become the exporter of green hydrogen in future. That is the anticipation. And one of the biggest advantage of green hydrogen is that it reduces the emission of carbon dioxide into the atmosphere, thus contributing to reducing the greenhouse effect. India has also come out with the ethanol blending targets that has enumerated that it would achieve 20% ethanol blending with petroleum by this year, 2025. Also, India has given a lot of importance to carbon storage and capture, CCS, in order to improve or in order to reduce its GHGs before they enter the atmosphere. So, there is large scale planning in India in the sectors of energy and electricity, mobility, transport and mobility. India is moving fast towards EV, electric vehicles. Then in terms of urban planning and design, also reducing embodied carbon emissions in industry, then in forestry, increasing greenery and having sequestered carbon. So, uh, policies, regulations, initiatives are also a great way for us to start reducing our embodied carbon and also operational carbon. And for architects, there are a number of codes if we follow. As I told you, ECBC code, Eco Nivas Samhita, the rating of buildings is also done by BEE, which is not becoming very popular, but there is green building rating system by various bodies like Lead India, Griha, Edge and so on. And also India is forging fast ahead in trying to respect sustainable development goals. So, all this must be comprehensively viewed by architects and designers. Another area where there is a large amount of carbon emission is in the structural systems. Because if you see, concrete is the most widely used construction material in the world, and that is responsible for 6 to 10% of GHG emissions. Portland cement is the primary ingredient of concrete, and that is responsible for the majority of concrete's greenhouse emissions. Roughly about 40% of concrete's greenhouse emissions are from burning fossil fuels, because that is what is used in the manufacturing process, and the remaining 60% comes from naturally occurring chemical reactions during the processing of cement. The proportion of ingredients in a concrete mixture can greatly influence its carbon impact, such as replacing this cement with some other materials, like limestone calcined clay or fly ash or GGBS, ground granulated furnace slag, blast furnace slag. All this can reduce the embodied carbon of concrete because we can use less cement in that concrete. Of course, we should use less concrete itself, that's the first given. But if we have to, say like in this aspect where we are looking at structural systems, then if concrete is mandatory, at least try to use concrete which is slightly green. Another area is masonry. Now, despite its very high embodied carbon intensity, by default, masonry construction method such as using modern brick construction, this has developed from a straightforward brick and mortar approach to more complex systems involving various other accessories. The embodied carbon of a masonry comes from two streams: the concrete manufacturing and processing stream and the brick firing stream. So, what I mean by that is, what is the source of fire for firing your clay blocks to become brick? That determines largely the embodied carbon of brick. So, in order to do that, we need to reduce embodied carbon of masonry by using some other less embodied energy material such as CSEB blocks or rammed earth instead of kiln fired bricks. We can also use reclaimed or salvaged bricks. Another third component which can really increase the embodied carbon of structural systems is steel, because steel has high embodied carbon due to its energy intensive manufacturing process. Steel is manufactured in two types of factories. So, you have large steel mills which typically use basic oxygen furnaces which burn coal or natural gas to extract iron by melting iron ore and then mix the iron with scraps of iron and steel to make new steel. Smaller factories typically use electric arc furnaces to melt scrap iron and steel and process it into new steel. So, how can you reduce embodied carbon of steel? That can be done by using steel from electric arc furnaces and use salvaged or reclaimed steel or steel with high recycled content. Another one material which can actually add or reduce embodied carbon is structural engineered wood. So, there has been innovations in mass timber which has the potential to make carbon neutral buildings scalable. Trees are harvested and replaced, especially in US. More trees are being planted than harvested every year. This can produce mass timber which can sequester more carbon during their growth than what it emits to manufacture, transport and construct the timber product. Increased demand for sustainably sourced timber can incentivize active forest management, and this can avoid deforestation also through conversion of forest land into other useful areas. So, engineered wood panels can replace steel decking and concrete floor slab in many commercial structure. We can also have glue lamp columns which can replace steel and concrete columns in low rise or maybe mid rise segment also. So, these timber products have an added advantage as they are fire resistant and you can quickly assemble them. So, the global warming potential for structural frame options can be dramatically reduced by our proper choice of building materials. Like steel and composite materials can have a global warming potential of 210 kg carbon dioxide equivalent per meter cube, whereas steel and composite made with CLT floors, whereas in the first case it was precast slab. So, having CLT floors will reduce the total global warming potential, and it can come up to 170 kg carbon dioxide equivalent per meter cube if you are using 90% recycled steel and cross laminated timber sheets. Also, if you use say glue lamp frame and CLT floor, where you use glue laminated timber beams and columns with cross laminated timber sheets, also using ready mix concrete, your global warming potential can be 130 kg carbon dioxide equivalent per meter cube. But if you use steel frame and slim floor, which is like 90% recycled steel and ready mix concrete with 0% recycled binders, then your global warming potential can rise significantly to 340 kg carbon dioxide equivalent per meter cube. Also, if you see RC frame and flat slab where you are using 90% recycled steel and you use ready mix concrete with recycled binders, then your global warming potential can be 390 kg carbon dioxide equivalent. So, you can dramatically reduce by using timber or hybrid structures such as steel plus timber in your structural systems. Besides the choice of building materials, you can also look at structural systems. So, what happens is the transportation energy, knowingly or unknowingly, sometimes we do not even realize, can actually dramatically reduce the carbon dioxide reduction or greenhouse gas emissions. So, Here we have taken an example where this building, when they used CLT and glue lamp, the transportation energy graphically is only this much, whereas if it is CLT and steel, there is a slight increase in transportation energy, whereas steel and composite slabs increase the transportation energy component of greenhouse gas emissions significantly. And if RCC frame structure is used, then you can see there is double the energy that is emitted because of transportation. So, transportation energy can actually be a large component when it comes to embodied carbon emissions. Also, the choice of structural system is very important. Now, a study by Jay showed that with respect to carbon dioxide emissions, the relative average environmental impact of, say, CLT were the lowest. This is followed by TCC and RC, which is reinforced concrete. So, it was found that the CLTs emitted 75% less carbon dioxide compared to concrete, irrespective of the design conditions. When I say design conditions, I mean the span or the live load. Whereas, if you look at timber concrete composites, they emitted 50% to 70% less carbon dioxide compared to reinforced concrete as the span increased. When considering the carbon storage capacity of wood, the carbon dioxide emissions of cross-laminated timber and timber concrete composites were reduced by an additional 151% and 77% respectively. So, by using proper building material and choosing the appropriate building material, we can actually reduce the embodied energy considerably. If you see here, you can see what happens on an average when you use reinforced concrete, cross laminated timber or timber concrete composites. There is more than 150% reduction in embodied energy when you start using cross laminated timber. Then next thing you can do is you can start measuring your embodied carbon, because what can be measured only can be monitored for further reduction. So, there are a number of digital tools with which you can do embodied carbon assessment. You have the Athena Impact Estimator for buildings. It's a free software tool for conducting comprehensive life cycle assessment of buildings, because it draws on a very simple embedded database of regionally specific material and its life cycle data. This tool can allow for side-by-side comparison, providing a clear visibility into the impact of your design choices. Then we can have the carbon smart materials palette also. This is this is an attribute based design and material specification guidance, which is intended to connect designers and architects and specifiers with information about specific materials and actionable information about how to reduce embodied carbon during the design and construction process. Then we have the EC3, which is the Embodied Carbon in Construction Calculator. This is again an open source database that can house thousands of digitized third-party verified environmental product declarations or EPDs. This tool is very useful in providing transparency of information and comparing the carbon impact of different product options across similar material types. So, this embodied carbon in construction calculator can allow users to compare upfront, what is upfront carbon? A1 to A3 embodied carbon, and the impact of different building materials for that particular project. Of course, it is not to be used as a whole building life cycle assessment tool, but it can give you thumb rules of what material we should actually use. Then we have subscription based softwares also, like one click LCA, which will integrate with building information modeling, and it is an extensive database of materials which have EPDs or environmental product declaration to produce a life cycle assessment in any design stage of a project. What are EPDs, environmental product declarations? I will be teaching later on in this course. Like this, we can use several digital tools to understand what is the impact that our choice of building material is creating, and also we can try and see if we can use some other alternative for our choices. Then another thing that we can actually do is design for disassembly. I will be taking this in greater detail during this course. So, but I'll give you a brief hint because I'm trying to teach you how to comprehensively reduce embodied carbon or the impact of building on environment. So, the ability of a space to be modified is very important, and we have seen that during COVID times because of social changes, or we need to change the building when people start aging, or when there is climate change, when there are various scenarios like work from home, or when the household size varies. So instead of demolishing the building and constructing new one, which we said was the worst thing to do, because that was the first strategy we said, not to demolish. So when we look at that, then what is the other option? The other option can be, we can design a building completely for its disassembly and avoid unrecyclable materials and finishes. I will just show you smaller examples of what can be done. For example, when people age, we can already anticipate that and start designing buildings for wider doorways to accommodate wheelchairs. Lifts can accommodate them. Then we can have access to latches for the aging. Cupboard heights can be reconsidered for the aging. Also, we should have the ability to downsize spaces. So when people live in, say, 2000 square feet house during the prime of their life, they do not need such a big house as they age. So we should be able to downsize these spaces too, and also have flexible room functions. So, and then we should start looking at concepts of material passport and circularity. So slowly we are moving into circular economy in its real sense, which I will be dealing in greater depth in the future classes. So instead of viewing, so basically what this means, reuse of building materials or building as material banks, is instead of viewing materials as used up once, they are integrated into the building. So, can we look at the material in a building more as a temporary storage of that material, which later we can take and use it elsewhere? That is the concept of material banking. So, this is an offshoot of the principles of circular economy, because a circular economy encourages materials that are perpetually reusable or recyclable rather than a one-way track to landfill, because a waste, what we call as waste, is actually a misplaced resource. So, in that sense, we can look at material passport and circularity. We should also look at reuse of building material. There's a project BAMB, which is buildings as material banks. We will be looking at it in greater detail later on. Then this is a network of about 15 partners from 7 European countries who work together to realize the goal of circular economy for buildings. So this group is developing this idea that we should use materials passport, which is more about having data of every single material and product that we use in the building, which we should be able to track their attributes, and therefore we should give future users of that particular material or component how to deconstruct and reinstall them. So that information should be given, and what we could do is we could incorporate this information in the building information model BIM, or encode it directly on the product with certain ideas that could someday help create more mature markets, or markets which are accepting greatly towards reused material. And this can make the buildings no, non-destructible, in the sense the building can be brought down but the material will perennially remain and it will not end up in landfills. We will see more of this individually in detail in forthcoming classes. Then the other concepts that we could follow is we can integrate EPDs and global warming potential limits in the project. So what are EPDs? I will anyways conduct exclusive lectures on that as part of this course itself. Then we can source sustainable material. I am not getting more into building materials because I had told you that I am already conducting a separate course on building materials as a cornerstone to sustainability. Then we can evaluate cost and carbon in early design stage. One of the ways is to use various tools. As an architect, what are the strategies you could follow to reduce embodied carbon in the built environment? So, an architect's role is very important. I would say architect and designer's role is very important, and it starts right from pre-design or site selection stage itself. So, the role of an architect or designer is not is not something which starts only with design. So, if we look at pre-design and site selection, an architect should consider reusing an existing building before deciding to design a new building. He should assess soil type and determine options for the building's foundation, because some types of foundation use greater quantities of material than others. So, based on the soil type, the architect will be able to look at the foundation design, and I told you foundation contributes a lot to embodied energy, should not underestimate that. Then he can consider salvaging or reusing materials from a building that is to be deconstructed. Further, he can set an embodied carbon budget for the project based on life cycle analysis calculation for benchmark buildings or case studies. Then during the conceptual or schematic stage, an architect can ensure that structural systems are compact, efficient and not oversized. He can design flexible and efficient spaces that allow for long-term changes in use. He can design for future disassembly and reuse. I have told you this is a very important domain of circularity, and I will be taking exclusive classes on this later on during the course. He should consider the embodied carbon of traits related to architectural design decisions such as massing, envelope system, foundations, landscaping, use of simple passive tools, advanced passive tools, etc. He should conduct an initial whole building life cycle assessment or perform a life cycle assessment for hotspot materials or assemblies with higher carbon intensities. I had briefly told you what alternatives or options an architect has the choice to take. He should select building systems and assemblies that minimize embodied carbon. Further, an architect can assess availability of local reused or locally sourced material which can dramatically reduce embodied carbon emissions. During the design, development and construction phase, an architect can specify material characteristics that results in low embodied carbon. He can substitute like for like materials that can offer lower GWP or lower global warming potential. He can consider the embodied carbon trade-offs related to architectural and structural refinement and changes, and he should update the whole body and he should update the whole building LCA as needed. So, if you see in all this, the maximum role is for architects and designers. Next, he should be able to incorporate clear embodied carbon goals in all procurement language and set building systems or material specific goals. An architect should include requirements for product substitution in the specification itself. An architect should request embodied carbon data including EPDs. What are EPDs? I will take in detail from all vendors. He should include previous work, experience and proposed solutions that address embodied carbon in any procurement selection criteria. Besides, an architect should design a subcontractor selection process that incentivizes bidders to offer low embodied carbon materials and methods. During the construction phase, an architect should establish clear guidelines and targets to reduce construction waste. An architect should hold contractors accountable for delivering low carbon design committed in the previous phases. An architect should document the as-built embodied carbon content of the building and publish this data. An architect should update the whole building life cycle assessment as needed. During the occupancy and maintenance phase, which normally does not take too much importance in our country, it is actually very important. The architect should debrief and apply lessons learned to the future projects. Besides, he should establish embodied carbon reduction targets for future renovations and tenant fit outs. So, this is the role of an architect, designer, civil engineer, builder in their contribution to lowering embodied carbon and lowering global warming potential through appropriate choice of building design and building material. With this, I will stop today's class on how can embodied carbon be reduced, resulting in lowering use of carbon intensive building material, and slowly how we will be transitioning to understand and learn about circular economy and EPDs, environment product declarations and so on. With this, we will stop today's class and we will meet next class with another interesting topic. Until then, thank you.